Hello and welcome to video 2. We are still going to talk about some things that we learned from secondary 4, and then we're going to start touching on just a few concepts from junior college. And as usual, we'll wrap things up with a practice question so we can reinforce the concepts that we've gone through in this video. Let's get started. Coordinates versus column vectors. So if I have a vector that starts from, say, the origin to some point, so if you want to write this down as a coordinates, you can write it as the x and y coordinates, which we know very well by now, or you can write it as a column vector. So the column vector is just writing the same numbers vertically and without comments. How to find the magnitude of a vector? So that we can use Pythagorean's theorem. It's very similar to coordinate geometry again in secondary 3, where if you want to find the distance from one point to another, you would use the Pythagorean's theorem, and that actually is the same for vectors. Good news is that although we are moving on to 3D vectors in JC, in H2 Maths, it is a bit more complex, but the distance formula is actually the same. You kind of just do x squared plus y squared and just add a z squared at the back. Unit vectors. So unit vectors are vectors who have a size or magnitude or length of 1. So why do we bother with these kind of things? Why do we want to make vectors with size 1? The motivation why we want to do this kind of things. First, we know that vectors and scalars, the difference is that vectors have size and direction, while scalars have size and no direction. But what if I wanted something with a direction but no magnitude? And then there comes the idea of a unit vector. Okay, so just to clarify, the unit vector has a magnitude, but it has a magnitude of 1, which is quite a neutral number. We'll see why that is a neutral number later on. So really the motivation behind unit vectors is to convey the sense of direction. With that, I can lead into another concept that we learned in JC, and that is the IJK vectors. You can also call them IJK directions. First of all, let me just introduce what are IJK. IJK are unit vectors in the direction of x, y, and z respectively. So if you have a column vector, for example 3, 2, 1, you can also express that as 3 steps in the x direction. Okay, so instead of saying 3 steps in the x direction, you can say 3i, 2j, 2 units along the y-axis, and then k, 1 unit in the z direction. Really, unit vectors are quite useful in conveying the direction. Again, these are very subtle things. Over time, as you do more practices, you'll start to understand these nuances. Let's wrap this all up with a practice question. So this is the practice question. You may pause the video, take out a pencil and paper and give it a try. Welcome back. This question is asking for a vector p, but we're only given 2 pieces of information. Number 1, p has a magnitude of 6. Okay, we like to use this notation, right? Depending on how far you are along your JC mathematics. This one is called a modulus function. So let me just introduce very quickly for those who do not know. So a modulus function is something that removes direction. For example, if I put a modulus of -5, that actually gives me 5. If I put a modulus of 5, it also gives me 5. So basically, it's only interested in the size, the magnitude, the number. It does not care about the direction, the minus sign or the plus sign. It just gives you a positive number all the time. So if I do a modulus p, what I'm doing is I'm de-vectorizing, or I'm scalarizing the vector to give you a scale, to give you just a number without a direction. Yes. So p has a magnitude of 6 and is in the direction of this one, which means that it is parallel to this other vector, which is 2, -3, 6. So I've gone ahead and calculated the magnitude of 2, -3, 6. That is 7. 2, -3, 6. Although it is parallel to p, I cannot call this p because they do not have the same magnitude. Remember that vectors are only the same if they're the same size and same direction. Given these 2 information, I have to find what is, say, A, B, and C. How do I do that? So first of all, maybe we can find the unit vector that is in the direction of 2, -3, 6. So again, I want you to imagine a unit vector to be something like this, right? That is in the same direction as, say, the red vector, but it's only 1 out of 7 the size of the red vector. Or you can think of, if I have 7 of these purple lines joined end to end, then it will form the exact same vector as the red one. So the question is, how do I find this purple vector? I'm going to call this red vector maybe Q. So to find the unit vector, the purple one, I can call it Q. Since it's a unit vector, we like to write it with a small little cap on top. So we call this Q cap. Q cap is equals to Q divided by the size of Q, which is equals to 1 out of 7 times of Q. So how do I have a 1 over 7 times a vector? So what you do is you take 1 over 7 and multiply each of the numbers inside your vectors. What that gives you is 2 over 7, negative 3 over 7, 6 over 7. And I just want to do a very quick check to see whether the size of Q cap, to check whether this is equals to 1. We all know that this is all over 7 square, so that's over 49. So 2 square is 4, negative 3 square is 9, and 6 square is 36. 4 plus 9 plus 36 is 49. Square root of 1, which is just 1. So yes, our vector here, Q cap, right, just by taking the vector Q and dividing by the size of Q will give us a unit vector. Now, to find out what is P, P is basically 6 of these purple vectors joined end to end. So what I can do is say that P is equals to 6 times of Q cap and 36 over 7. And that is the answer to this question. So I hope you found this video helpful, and I'll see you in the next video where we talk about dot product, one of the most useful tools we'll learn in vectors for H2 Maths. So until then, I'll catch you on the flip-flop.